Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold reaches of interstellar space, where a visitor from another star system announces itself in ice and light. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. The comet crosses the orbital plane on a trajectory that belongs to no family tree in our solar system. Its path curves through the ecliptic at an angle too steep, its velocity too high, its origin stamped in the mathematics of hyperbolic geometry. Astronomers notice it first as a smudge of light that refuses to behave, a faint glow that brightens as it approaches the sun, trailing a coma of sublimating ice that catches photons and bends them into a tail. The tail, they notice almost immediately, does not point symmetrically away from the sun. It leans, it favors one side, as if the comet itself remembers some ancient preference, some structural bias written into its nucleus billions of years ago, in a star system whose light has never reached Earth. The discovery comes through automated surveys, through telescopes that sweep the sky in grids, cataloging transients and measuring positions with patient precision. Only after several nights of observation does the orbital calculation resolve into certainty this object is not bound to our sun. Its eccentricity exceeds 1. It came from elsewhere, from the space between stars, and it will return there, carrying with it whatever secrets its ice holds. The announcement spreads through the astronomical community with the kind of quiet urgency reserved for phenomena that rewrite textbooks without fanfare. There have been only a handful of confirmed interstellar visitors. Each one is a messenger from the galaxy's deeper architecture, a fragment of some distant planetary system's failed accumulation, cast out into the void and wandering for epochs beyond human comprehension. The comet's brightness increases as perihelion approaches. Sunlight warms its surface, heating frozen volatiles that have remained inert for millions of years. Water ice sublimes directly into vapor, bypassing the liquid phase entirely in the vacuum of space. Carbon monoxide follows, then carbon dioxide, then trace amounts of cyanogen and methane, a chemical inventory that speaks to the conditions of its birth. Spectrographs dissect the light reflected from the coma, revealing absorption lines that match those of comets born in our own Kuiper belt and Oort cloud. The chemistry is familiar. The asymmetry is not. On one hemisphere, gas jets erupt with vigor, spewing molecules into space at velocities measured in hundreds of meters per second. On the other, silence, or near silence, a trickle of outgassing so faint that instruments struggle to detect it above background noise. The imbalance is not subtle. It is pronounced, persistent, and maddeningly resistant to easy explanation. Models predict that a rotating nucleus heated by the sun should outgas symmetrically over time, averaging out any small-scale variations as different latitudes face the star. But this comet does not average out. It maintains its preference, its lopsidedness, even as it tumbles through space. Theories emerge almost immediately, each one plausible, none fully satisfying. Perhaps the nucleus is not homogeneous. Perhaps one side is rich in volatiles while the other is mantled in dust, insulated against solar heating. Perhaps the rotation axis is tilted in such a way that one pole remains perpetually shadowed, a frozen relic of its interstellar journey. Perhaps subsurface voids channel gas along preferential pathways, creating jets that emerge from specific latitudes while leaving others dormant. Or perhaps, and this is the quietest suggestion, the one that appears in footnotes and late-night email exchanges, something happened to this comet before it entered our solar system. Some encounter or event that scarred it, modified it, left it asymmetric in ways we have not yet imagined. The observations continue. Telescopes across the world coordinate their schedules, capturing images in multiple wavelengths, measuring the rotation period, tracking the evolution of the coma as the comet swings around the sun. Data accumulates, parameters refine, and still, the asymmetry persists, a quiet riddle written in ice and gas, a phenomenon that should not be mysterious but somehow is. It took billions of years for this object to cross the galaxy and arrive here. It will take perhaps a few more decades before we understand why it outgasses the way it does. Time, as always, remains unbothered by human curiosity. The comet does not know it is being watched. It does not know it has a designation, a catalog number, a growing file of observations and models and competing hypotheses. It simply continues, obeying the laws of thermodynamics and orbital mechanics, shedding molecules into space with an imbalance that may be accidental, structural, or most intriguingly, the signature of processes we have not yet named. The geometry of the comet's approach is written in numbers that reveal its alienness with quiet precision. Its velocity at infinity, the speed it would maintain if no gravitational field existed, to slow or redirect it, exceeds the escape velocity of the solar system by a comfortable margin. This is the signature of an interloper, a wanderer that owes no allegiance to our sun's gravity well. Orbital elements are calculated and recalculated as more observations arrive. Eccentricity well above unity. Inclination steeply tilted relative to the plane where planets circle. A semi-major axis that extends backward into negative space. A mathematical abstraction indicating an orbit that never closes, never repeats, never returns. Astronomers trace the trajectory backward through time, rewinding the comet's path through the decades and centuries it spent approaching us. The calculation is straightforward, but haunted by small uncertainties. The gravitational nudges from Jupiter and Saturn, the radiation pressure from sunlight pushing against gas and dust, the rocket effect of asymmetric outgassing itself, which accelerates the nucleus in unpredictable directions. Despite these complications, the general picture emerges. This object has been falling toward the sun for thousands of years. Its path shaped by a velocity vector it carried from interstellar space, a momentum inherited from whatever event ejected it from its birth system. The discovery images show a faint streak, barely distinguishable from background stars, moving at a rate that seems unremarkable until one calculates the distance. At several astronomical units from Earth, even a modest angular motion translates into extraordinary velocity. Confirmation requires multiple nights of observation, during which the comet's position shifts against the celestial backdrop in a manner consistent with a hyperbolic trajectory. Orbital determination is an iterative process, a refinement of parameters through least squares fitting, a gradual convergence toward truth as more data points accumulate. The first preliminary orbits are uncertain, their error bars wide. By the second week, the hyperbolic nature is probable. By the third, it is certain. Telescopes around the world receive alerts through automated networks, systems designed to recognize and prioritize transient phenomena. Follow-up observations are scheduled, competing with other programs, other targets, other uses of expensive mirror time. The comet is faint, requiring long exposures and careful tracking to compensate for its motion. Larger instruments are brought to bear 8-meter mirrors in Chile and Hawaii. adaptive optic systems that correct for atmospheric turbulence, spectrographs that split light into constituent wavelengths. Each observation adds a data point, a constraint, a piece of the puzzle that is both the comet's past and its present behavior. The rotation period is measured through photometry, watching the nucleus brighten and dim as different faces turn toward Earth and Sun. The period is irregular, suggesting a non-principal axis rotation, a tumbling motion rather than a clean spin. This is common among small bodies. Collisions and outgassing torques over geological time disrupt simple rotation, leaving nuclei wobbling through space like cosmic footballs. The irregularity complicates models of surface heating, making it harder to predict which regions will receive the most sunlight at any given moment. And yet, despite this complexity, the outgassing asymmetry remains consistent, as if locked to some structural feature rather than driven purely by insolation patterns. The comet's size is estimated from its brightness and assumed albedo. Cometary nuclei are dark, reflecting only a few % of incident sunlight, their surfaces coated in refractory organics left behind as volatiles sublime away. Using typical albedo values, astronomers calculate a nucleus perhaps a few hundred meters across, small enough to fit within a city block, large enough to contain billions of tons of ice and rock. The uncertainty is large, a factor of 2 or more in either direction, but the rough scale is sufficient for modeling purposes. This is not a giant among comets, not a Hale-Bopp or a Halley. It is modest, unremarkable in size, distinguished only by its origin and its strange reluctance to outgas evenly. Astrometric measurements track the comet's position with sub-arc-second precision, feeding into orbital models that predict its future trajectory. The path is clear. Perihelion will occur in a few months. A closest approach to the Sun at a distance inside Earth's orbit, followed by a long, accelerating departure. Within a year or two, the comet will fade beyond the detection limits of even the largest telescopes, receding into the outer solar system and eventually back into interstellar space. The window of observation is narrow. Whatever can be learned must be learned quickly, before the visitor returns to the darkness between stars. There is something quietly absurd about the logistics. Millions of years in transit, drifting through the galaxy at speeds measured in kilometers per second, exposed to cosmic rays and the faint glow of starlight. And the comet finally arrives here, now, at a moment when humanity possesses telescopes capable of noticing it. A few centuries earlier, it would have passed unseen. A few centuries hence, our instruments might be sensitive enough to detect such objects while they are still in the outer solar system, years before perihelion. But it arrives precisely in this narrow epoch, crossing paths with a technological civilization young enough to find it remarkable, old enough to measure it with care. The timing, like the asymmetry, invites questions that have no clear answers. The comet does not adjust its course in response to observation. It continues inward, indifferent to the growing file of measurements and models, the conference presentations and preprint servers filling with papers that attempt to explain what it is doing and why. Geometry is destiny, and its destiny was written in the dynamics of some distant planetary system, in the gravitational slingshot or stellar encounter that sent it here. All we can do is watch, measure, and wonder. Spectroscopic fingerprints begin to accumulate as the comet draws closer to the Sun and its coma brightens. Light reflected from the cloud of gas and dust surrounding the nucleus is collected by telescope mirrors, focused into fiber optic cables, and dispersed through diffraction gratings that spread wavelengths across detector arrays. The resulting spectrum is a landscape of absorption and emission lines, each one corresponding to a specific molecular transition, a quantum leap of electrons between energy states. Water vapor dominates. As expected, H2O is the most abundant volatile in comets formed in cold regions of protoplanetary disks. The hydroxyl radical, appears strongly in ultraviolet wavelengths, a dissociation product of water molecules torn apart by solar radiation. Carbon monoxide shows up in infrared observations, its rotational lines crisp and unambiguous. CO is more volatile than water, subliming at lower temperatures, which means it can outgas from regions still too cold for water ice to evaporate. The ratio of CO to water is measured carefully, providing clues about the temperature profile of the protoplanetary disk where this comet formed. High CO to water ratios suggest formation in the coldest regions, far from the central star, where even carbon monoxide can freeze. This comet's ratio is moderate, comparable to some Jupiter family comets in our own system, suggesting it formed in a region analogous to our outer solar system cold, but not the coldest. Cyanogen appears as well, the CN radical glowing in visible wavelengths with a distinctive violet hue. Its presence is expected. Cyanogen is common in cometary comet, a product of more complex organic molecules breaking down under solar ultraviolet light. Methane is detected in smaller quantities, along with traces of ammonia and formaldehyde, a chemical inventory that speaks to the diversity of ices that condensed in the comet's birth cloud. Each molecule is catalogued, its abundance measured relative to water, its spatial distribution mapped across the coma. The asymmetry appears here too. The coma is brighter on one side, denser with molecules, indicating that the outgassing source is localized rather than global. Dust particles are analyzed through their continuum emission, the broad background of reflected sunlight that underlies the sharp spectral lines of gas. The dust grains are small, submicron to micron-sized, composed of silicates and carbonaceous material, particles that formed in the cooling envelope of some ancient star and were later incorporated into the comet during its accretion. The dust-to-gas ratio is estimated from the relative brightness of continuum and emission lines, a quantity that varies widely among comets and reveals something about the structure and composition of the nucleus. This comet's dust-to-gas ratio is higher on the active hemisphere, suggesting that whatever process drives the asymmetric outgassing also preferentially lofts dust into space. Comparisons are drawn immediately to comets native to our solar system. The spectral signatures are remarkably similar if one did not know the orbital elements. One might assume this was a long-period comet from the Oort cloud, an object formed 4.5 billion years ago in the same disk that birthed the planets. The chemistry is not exotic. The molecules are the same ones found in comets observed for centuries. This sameness is itself profound. It suggests that the processes of planet formation, of ice condensation and volatile trapping, operate similarly around different stars. The building blocks are universal, governed by the same physics, the same thermodynamics, regardless of which stellar nursery they emerge from. And yet, subtle differences are sought with intensity. Are there isotopic anomalies, deviations in the ratios of deuterium to hydrogen, nitrogen-15 to nitrogen-14, carbon-13 to carbon-12? Such variations could encode information about the temperature and radiation environment of the comet's birth cloud. The supernova shockwaves that may have enriched its parent molecular cloud with heavy elements. The specific conditions that distinguished its formation from that of solar system comets. The measurements are difficult, requiring high spectral resolution and long integration times. Preliminary results suggest isotopic ratios within the range seen in solar system objects, but uncertainties are large. More observations are needed. and time is running out as the comet approaches perihelion and its coma becomes increasingly crowded with gas and dust. The spectrum is not static. It evolves as the comet's distance from the Sun decreases, as different ices reach sublimation temperature, as solar heating penetrates deeper into the porous nucleus. Water dominates near perihelion, but farther out, CO and CO2 may have been the primary drivers of activity. Observers note that the asymmetry predates the water-dominated phase. It was present even when the comet was distant and faint, when only the most volatile species were subliming. This suggests the asymmetry is not solely a function of solar heating patterns, but may be intrinsic to the nucleus itself, a consequence of its composition, structure, or history. There is a quiet irony in the fact that spectroscopy, a technique developed in the 19th century to study the chemistry of flames and stars, now reveals the composition of an object that has spent millions of years isolated in the void between stellar systems. The same quantum mechanics that governs laboratory experiments governs the coma of this interstellar visitor. Physics does not respect origin stories. The photons do not care where the molecules came from. They simply interact, scatter, absorb, emit, carrying information encoded in wavelengths and intensities, waiting patiently for instruments and minds capable of decoding them. The data accumulates in archives, terabytes of spectra stored on servers, available to anyone with the inclination to analyze them. Each observation is time-stamped, annotated with telescope coordinates and detector specifications, reducible to tables of flux versus wavelength. The comet becomes, in part, a dataset, a collection of numbers that will outlive the physical object itself, which will eventually fade beyond detection and return to the darkness. But for now, the light continues to arrive, carrying messages written in molecular transitions, in the language of quantum mechanics, in the universal chemistry of ice and dust. The puzzle of uneven sublimation becomes the central mystery. The feature that transforms this interstellar visitor from merely interesting to genuinely perplexing. Standard models of cometary activity predict that a rotating nucleus exposed to sunlight should, over multiple rotations, outgas in a manner that averages towards symmetry. As different portions of the surface turn to face the sun, each region receives its share of heating, each patch of ice its opportunity to sublime. Variations exist. Certainly topographic features like craters or ridges can cast shadows, alter local temperatures, create jets that emerge from specific locations, but such variations typically smooth out over time, producing a coma that appears roughly spherical when viewed over periods of hours or days. This comet refuses to smooth out. Observations spanning weeks show the same pattern, one hemisphere active, the other largely dormant. The active region releases water vapor, carbon monoxide, dust, and trace species in quantities that match or exceed expectations for a nucleus of this size. The quiet hemisphere releases almost nothing, or at least nothing detectable above instrumental noise thresholds. The boundary between active and inactive is not sharp. There is no line drawn across the surface, but the gradient is steep enough to be unmistakable in the data. Gas production rates are calculated for different rotational phases, and the asymmetry persists regardless of which face points toward the sun at any given moment. One hypothesis proposes that the nucleus is composed of two distinct lobes, joined in a contact binary configuration, each lobe having formed separately and later merged through gentle collision. Such structures are known from solar system comets 67P Churyumov-Gerasimenko, studied extensively by the Rosetta spacecraft, exhibited precisely this morphology. If the interstellar comet consists of two bodies with different compositions, perhaps one rich in volatiles and the other depleted. The asymmetry would be explained. But contact binaries typically show some activity from both lobes, even if unequal. Complete dormancy of one component would require extreme compositional differences. A scenario not impossible, but requiring special pleading. A stacking of coincidences that makes theorists uneasy. Another hypothesis focuses on surface layering. Cometary nuclei are known to develop dust mantles, layers of refractory material left behind as volatiles sublime away. These mantles insulate the ice beneath, slowing or halting sublimation even when sunlight is abundant. Perhaps one hemisphere of the nucleus acquired a thicker mantle during its interstellar journey, coated by fine dust lofted during some earlier active period, or perhaps even modified by bombardment with interstellar grains over millions of years. The mantle would need to be thick enough and thermally insulating enough to suppress outgassing entirely a few centimeters at least, possibly more. This is plausible but difficult to verify without a spacecraft flyby, which for an interstellar comet on a hyperbolic trajectory remains purely hypothetical. Thermal inertia. The resistance of a material to temperature changes enters the discussion. Low thermal inertia means that surface temperatures respond quickly to solar heating and cool rapidly when shadowed. High thermal inertia means that heat diffuses into the subsurface, creating a thermal wave that can drive sublimation from depths of centimeters or even meters below the surface. If the two hemispheres have different thermal properties, perhaps due to variations in porosity or grain size or composition, they would respond differently to the same solar input. One side might reach sublimation temperature quickly and efficiently, while the other lags behind, remaining cold enough that volatiles stay frozen. The math is consistent with observations, but the origin of such a hemispheric dichotomy remains unexplained. Rotation, axis orientation adds another layer of complexity. If the comet's spin axis is tilted such that one pole remains in perpetual shadow during the months of observation, that pole would stay cold, its ice preserved in a frozen state even as the equatorial and opposite polar regions heat up. Seasons on comets, like seasons on planets, depend on axial tilt and orbital geometry. A comet with high obliquity, a spin axis nearly perpendicular to its orbital plane, can experience extreme seasonal contrasts, with one hemisphere baking in continuous sunlight while the other languishes in darkness. This scenario is geometrically possible but statistically unlikely, requiring a specific alignment between rotation axis, orbital plane, and observation epoch. It also fails to explain why the asymmetry was present even when the comet was far from the Sun, when seasonal effects should have been negligible. The mystery invites speculation, but speculation constrained by physics. Wild theories are proposed in online forums and amateur astronomy groups, magnetic fields frozen into the nucleus, electric currents driven by solar-wind interactions, even suggestions of artificial origin, which are promptly dismissed by anyone familiar with the spectroscopic evidence. The comet is ice and rock, molecules and dust, governed by thermodynamics and gravity and nothing more exotic. Its asymmetry is real, measurable, and strange. But strangeness is not the same as impossibility. Nature produces asymmetries all the time, through processes mundane and well understood. The challenge is identifying which process, or combination of processes, applies here. What bothers researchers most is not the asymmetry itself, but the lack of a smoking gun, a single clear mechanism that explains all observations without residual puzzles. Every hypothesis fits some data and struggles with other data. Every model produces a symmetry, but not quite the right asymmetry. not with the right spatial distribution or temporal evolution. The comet offers a lesson in humility even with modern instruments. Even with decades of cometary science to draw upon, nature can present phenomena that resist easy interpretation. It took billions of years for the comet to arrive. It may take a few more decades for a fully satisfying explanation to emerge. Or perhaps the next interstellar visitor will behave differently, offering comparison data that clarifies what this one leaves obscure. Rotation and the memory of formation intertwine in ways that blur the boundary between past and present. The nucleus spins, tumbling through space with a period measured in hours, each rotation carrying it through cycles of sunlight and shadow, heating and cooling, activity and quiescence. But this rotation is not new. It is ancient, inherited from the processes that assembled the comet billions of years ago, modified slightly by collisions and outgassing torques over geological time, but fundamentally unchanged in character. The spin axis points in a direction determined by the angular momentum of the cloud of gas and dust from which the comet accreted, a vector that has remained roughly constant through millions of years of interstellar drift. Non-principal axis rotation complicates the picture. Rather than spinning smoothly around a single axis, the nucleus wobbles, precessing slowly through space in a motion that makes prediction difficult. This tumbling is common among small, irregularly shaped bodies, asteroids, cometary nuclei, fragments of larger objects shattered by impact. The energy for this motion comes from the comet's formation, from the chaotic accretion of smaller particles that did not settle into a neat, symmetric configuration. Once established, tumbling is difficult to damp out. In the absence of atmosphere or significant tidal forces, angular momentum is conserved, and the nucleus continues its complex rotation indefinitely. Observations capture this tumbling in the form of light curves, plots of brightness versus time that show periodic variations as different portions of the nucleus reflect sunlight back toward Earth. The light curve is not sinusoidal but irregular, with multiple peaks and troughs per rotation, suggesting an elongated or bilobed shape. Sophisticated inversion techniques attempt to reconstruct the three-dimensional form of the nucleus from these one-dimensional brightness variations, but the solutions are non-unique. Many different shapes can produce similar light curves, especially when viewing geometry is limited to a narrow range of angles. The best that can be said is that the nucleus is probably elongated, probably irregular, probably tumbling, and definitely not spherical. The surface of the nucleus bears scars from its time in interstellar space, though these scars are invisible to telescopes observing from Earth. Cosmic rays have bombarded the ice for millions of years, high-energy particles that penetrate centimeters into the subsurface, breaking molecular bonds, creating radicals and new chemical species, altering the structure of the ice lattice itself. Interstellar grains, dust particles drifting through the galaxy at velocities of tens of kilometers per second, have impacted the surface, each collision excavating a microscopic crater, sputtering atoms into space, gradually eroding the outermost layers. These processes are slow, glacially slow by human standards, but over millions of years they accumulate, modifying the surface in ways that might, perhaps, contribute to the observed asymmetry. One hemisphere may have faced forward during the comet's interstellar journey, exposed more directly to the rain of cosmic rays and interstellar dust, while the other trailed behind, partially shielded by the nucleus itself. This would create a difference in surface processing, a gradient in radiation damage and erosion that could translate into differences in thermal or mechanical properties. Forward-facing surfaces might be more compacted, their ice structure altered by radiation, making sublimation more difficult. Or the opposite might be true. Radiation could create a more porous, fluffy structure that sublimates more readily. The physics of these processes is poorly constrained, studied mostly in laboratory experiments that struggle to replicate the extreme timescales and low temperatures of interstellar space. The rotation period itself is a clue, a parameter that encodes information about the nucleus's shape, density, and structural integrity. If the period is too fast, centrifugal forces would overcome the weak self-gravity of the small nucleus, tearing it apart. The observed period is comfortably below this limit, indicating a coherent body rather than a loosely bound rubble pile. But comets are known to be fragile, their interiors filled with voids and fractures, their strength measured in tens or hundreds of pascals rather than megapascals. The nucleus holds itself together through a combination of weak ice cohesion and self-gravity, a balance that can be disrupted by thermal stress, tidal forces, or the rocket effect of outgassing itself. Outgassing torques alter rotation over time. Each jet of gas leaving the surface carries momentum, exerting a small force on the nucleus, a rocket effect that can spin the body up or down depending on the geometry of the active regions. For a symmetrically outgassing comet, these torques average out, but for an asymmetric comet, they accumulate, gradually changing the rotation period and potentially even the orientation of the spin axis. Observers watch for these changes, measuring the rotation period with increasing precision as more data arrives, searching for the telltale signature of torque-induced spin evolution. So far, no clear trend is detected, but the observation baseline is short a few months compared to the millions of years the comet has existed. There is something quietly profound about the fact that the comet's rotation remembers its birth. Every spin is an echo of the processes that occurred in a protoplanetary disk orbiting a star we cannot name, in a stellar system we cannot locate, at a time when Earth itself was perhaps still forming or perhaps already ancient, depending on the age of that distant system. The rotation is a thread connecting past to present, a physical continuity that persists across galactic distances and geological epochs. And yet, despite this continuity, the comet remains inscrutable, its asymmetry unexplained, its structure unknown, its story incomplete. The nucleus does not reflect on its own rotation. It simply continues, obeying the laws of angular momentum conservation, turning through space with the same motion it has maintained since its formation. Time passes. Sunlight warms one face, then another, in a cycle that will continue until the comet departs our solar system and returns to the cold, returning once again to the darkness where rotation matters little and memory fades into the patient stillness of interstellar space. Theories of porous structure and thermal inertia proliferate as researchers attempt to model the asymmetry from first principles. The nucleus is assumed to be porous, filled with voids and fractures on scales ranging from microns to meters, a structure more akin to a frozen sponge than a solid block of ice. Porosity is ubiquitous among cometary nuclei measurements. From spacecraft missions suggest values of 50 to 80%, meaning that half or more of the volume is empty space. This porosity affects heat transport, slowing the diffusion of thermal energy from the sunlit surface into the interior, creating temperature gradients that drive sublimation from subsurface layers rather than just the surface itself. Thermal models are constructed, dividing the nucleus into three-dimensional grids of computational cells, each assigned temperature, composition, and thermal properties. Solar radiation strikes the surface, heating it according to the local angle of incidence, the surface albedo, and the emissivity in infrared wavelengths. Heat diffuses inward following Fourier's law, conducted through the ice and dust matrix at a rate determined by thermal conductivity, a parameter that depends on porosity, grain size, and the degree of contact between particles. Where temperatures exceed the sublimation point of volatile species, ice transforms directly to vapor, a phase transition that absorbs latent heat and cools the surrounding material, creating a self-regulating feedback loop. These models can produce asymmetry if the porosity or composition varies between hemispheres. A region with higher porosity has lower thermal conductivity, meaning heat penetrates less deeply, keeping subsurface ice cooler and reducing sublimation rates. Conversely, a denser region with better grain-to-grain contact conducts heat more efficiently, allowing thermal energy to reach deeper ice layers and drive more vigorous outgassing. The challenge is explaining how such a hemispheric dichotomy in porosity could arise. During formation, accretion processes tend to be relatively uniform, building up layers of similar structure across the entire nucleus. Subsequent evolution might create variations, but mechanisms are elusive. One possibility involves differential sintering, the process by which ice grains coalesce and densify over time when held near their sublimation temperature. If one hemisphere spent more time at elevated temperatures during some earlier epoch, perhaps during a previous passage near a star. If the comet was once in a bound orbit before being ejected, that region could have sintered more thoroughly, reducing porosity and increasing thermal conductivity. The opposite hemisphere, remaining cold, would retain its original fluffy structure. This scenario requires a specific thermal history, one that can be imagined but not proven without knowing the comet's complete trajectory through the galaxy. Another hypothesis focuses on compositional layering. Cometary nuclei are thought to consist of layers or regions with different ice-to-dust ratios, reflecting variations in the protoplanetary disk during accretion or mixing of materials from different radial distances. If one hemisphere is ice-rich and the other dust-rich, their thermal and sublimation properties would differ significantly. Ice-rich regions sublime readily, producing jets and coma. Dust-rich regions form mantles that insulate the ice beneath, suppressing activity. The boundary between these regions might be internal, a contact surface between two components that merged early in the comet's history, or it might be external, a dust mantle that preferentially accumulated on one side during some active period. Subsurface voids and channels add further complexity. Sublimation does not occur only at the surface, it can happen at depth, wherever temperatures and pressures reach the appropriate conditions. Gas produced in the subsurface must escape through pores and cracks, following pathways determined by the internal structure of the nucleus. If these pathways are preferentially developed on one hemisphere, perhaps due to previous activity or structural weaknesses inherited from formation, gas might vent asymmetrically even if sublimation occurs throughout the nucleus. The result would be jets emerging from specific locations, creating the appearance of localized activity when in reality the source region is distributed. Mechanical strength, or the lack thereof, influences how the nucleus responds to thermal stress. As ice sublimates and gas pressure builds in subsurface voids, stress accumulates. If the overlying material is weak, it can fracture, creating new pathways for gas escape and potentially exposing fresh ice to sunlight. If it is strong enough to resist fracturing, pressure builds until it either forces gas through existing pores or eventually causes a more dramatic failure, an outburst or splitting event. The Interstellar comet has not been observed to split, but the observation window is limited. Such events, if they occur, could reset the asymmetry or amplify it, depending on where and how the nucleus fractures. Numerical simulations run for days on computing clusters, iterating through parameter space, searching for combinations of porosity, conductivity, composition, and structure that reproduce the observed asymmetry. Some combinations succeed reasonably well, matching the overall pattern of activity and dormancy. Others fail spectacularly, producing symmetric comet or wildly varying activity levels that contradict observations. The successful models are not unique. Multiple parameter sets can produce similar results, a degeneracy that reflects the fundamental problem of inferring three-dimensional structure from two-dimensional observations. Without a spacecraft mission to directly measure the nucleus's properties, these ambiguities will persist. There is a certain satisfaction in the fact that thermal physics, developed initially to understand steam engines and industrial processes, now finds application in modeling objects formed billions of years ago around distant stars. The mathematics is the same. Heat diffusion obeys the same differential equations whether applied to a terrestrial furnace or an interstellar comet. Only the boundary conditions change, the specific values of temperature and thermal conductivity and sublimation rates. Nature is economical with its laws, reusing the same principles across vastly different contexts. It took centuries to develop the theory. It will take perhaps a few more decades to apply it successfully to this particular puzzle. Dust-to-gas ratios and particle drift offer another window into the asymmetry, a perspective that shifts focus from the nucleus itself to the material it ejects into space. Every molecule of gas that sublimates carries with it the possibility of lofting dust particles, tiny grains of silicate and organic material embedded in the ice matrix. As gas expands outward from the surface, drag forces entrain dust particles, accelerating them to velocities that depend on their size and the local gas density. Small particles, micron-sized or smaller, couple efficiently to the gas flow and are carried along at nearly gas velocities. Larger particles, millimeter-sized and above, couple poorly and may not escape the nucleus's weak gravity at all, falling back to the surface after brief ballistic trajectories. The dust-to-gas mass ratio is a fundamental parameter in cometary science, a number that encapsulates the relative abundance of refractory and volatile material. For solar system comets, this ratio varies from near zero for gas-rich objects to several times unity for dust-dominated comets. The interstellar visitor shows a dust-to-gas ratio that is higher on the active hemisphere, evident from the brightness of reflected sunlight in the coma and tail. More dust means more surface area reflecting photons, which translates directly into higher brightness in continuum wavelengths, the broad background underlying the sharp emission lines of gas species. This hemispheric difference in dust content could arise from variations in the ice-dust mixture within the nucleus. If one side contains more dust grains per unit volume of ice, sublimation from that region would naturally produce a higher dust-to-gas ratio. Alternatively, the difference might reflect the efficiency with which dust is lofted from the surface. A dusty mantle can trap grains, preventing them from escaping even as underlying ice sublimates and gas percolates upward through pores. Only where the mantle is thin or absent can dust be efficiently ejected. The active hemisphere might be a region where the mantle has been eroded away or never formed, exposing fresh ice and embedded dust to direct sublimation and ejection. Particle size distribution is inferred from the way dust scatters sunlight. Small particles scatter light efficiently at all wavelengths, producing a relatively flat spectrum. Large particles preferentially scatter longer wavelengths, reddening the reflected light. Observations in multiple filters, from ultraviolet through near-infrared, allow astronomers to constrain the size distribution, typically modeled as a power law where the number of particles decreases with increasing size. The interstellar comet's dust follows a distribution similar to that of solar system comets, another point of chemical and physical similarity despite the vast difference in origin. The tail itself is a record of ejection history, a tracer of where dust particles were when they left the nucleus and how they have since drifted under the influence of solar radiation pressure. Photons carry momentum, and when they reflect off or are absorbed by dust grains, they transfer that momentum, pushing the particles away from the sun. The magnitude of this radiation pressure force depends on particle size and composition, with smaller particles experiencing stronger acceleration relative to their mass. Over time, this differential acceleration sorts particles by size, creating a tail structure that encodes information about the dust ejection process. The asymmetric outgassing produces an asymmetric tail, one that does not point precisely anti-sunward, but is offset, bent by the asymmetric distribution of ejected material. Modeling the tail's shape requires tracing the trajectories of millions of individual dust particles, each launched from the nucleus at a specific time and location, each subject to solar gravity and radiation pressure, each drifting through space on a slightly different orbit. These so-called syndyne and synchrone models, developed decades ago for solar system comets, are applied to the interstellar visitor with mixed success. The general shape is reproduced, but fine details remain elusive, suggesting that the ejection process is more complex than simple radial outflow from discrete jets. Dust particles also interact with the solar wind, the stream of charged particles flowing outward from the sun at hundreds of kilometers per second. Although dust grains are electrically neutral, they can acquire charge through collisions with plasma ions and electrons, and through the photoelectric effect when ultraviolet photons eject electrons from grain surfaces. Charged grains experience forces from the solar wind's magnetic field, which can deflect their trajectories in ways that differ from purely gravitational and radiation pressure effects. These interactions are subtle but potentially measurable, adding yet another layer of complexity to the interpretation of tail morphology. The dormant hemisphere produces little dust, or at least little that escapes into the coma. This asymmetry is visible in images as a one-sided brightness enhancement, a fan or jet-like structure emerging from the active region while the opposite side remains dark. The boundary between bright and dark is not sharp but gradual, consistent with a gradual transition in activity level rather than a binary on-off switch. Over time, as the comet rotates and different faces point toward the sun, the location of the bright region shifts, but the overall asymmetry persists, always one side active, always the other quiet. There is an irony in the fact that dust, the least volatile component of the comet, provides some of the clearest evidence for the asymmetry in volatile outgassing. The ice itself is invisible to optical telescopes, known only through its dissociation products and the gas emission lines they produce. Dust, by contrast, reflects sunlight and can be imaged directly, mapped in 2 dimensions. Its spatial distribution measured with precision. The solid traces the gaseous, the refractory reveals the volatile, and the asymmetry that began as a puzzle in spectroscopy becomes visible as a lopsided plume of particles drifting through space. It took billions of years for the comet to arrive, and only months for dust grains to drift from nucleus to outer coma. Time, as always, operates on multiple scales simultaneously, indifferent to human attempts at narrative coherence. Comparative silence from the shadow hemisphere deepens the mystery rather than resolving it. The term shadow is metaphorical here. There is no permanent shadow in the sense of a region perpetually blocked from sunlight by topography or orientation. Rather, the dormant hemisphere receives sunlight during its rotation, faces the sun for hours at a time, absorbs solar radiation, and should, by all conventional reasoning, warm to temperatures sufficient for ice sublimation, and yet it does not respond, or responds so weakly that instruments strain to detect any activity at all. This silence is not the silence of darkness, but the silence of ice that refuses to behave as ice should. Upper limits on gas production from the dormant hemisphere are established through sensitive spectroscopic observations, measurements that place constraints on how much water vapor, carbon monoxide, or other species could be present without being detected. These limits are typically 1 to 2 orders of magnitude below the production rates observed from the active hemisphere, suggesting that if sublimation is occurring on the dormant side, it is at a level 10 to 100 times weaker. Such a difference cannot be explained by modest variations in solar illumination or surface temperature. Something more fundamental must be suppressing activity, a thick insulating layer, a compositional anomaly, or a structural difference that prevents gas from escaping even if sublimation occurs beneath the surface. One hypothesis proposes that the dormant hemisphere is mantled by a layer of dust and refractory organics several centimeters thick, material left behind as volatiles sublimed during some earlier active period. Perhaps millions of years ago, when the comet last encountered a stellar radiation field, this mantle would act as thermal insulation, keeping subsurface temperatures below the sublimation point of water ice even when the surface itself is warm. The mantle hypothesis is attractive because it explains both the lack of observed activity and the persistence of the asymmetry over multiple rotations. A dust layer, once formed, is difficult to remove without mechanical disturbance or erosion processes that operate on geological timescales. But the mantle hypothesis raises its own questions. How did the mantle form preferentially on one hemisphere and not the other, if both sides were exposed to similar thermal conditions during formation or during the comet's interstellar journey? Both should have developed mantles of similar thickness. Perhaps the answer lies in the comet's rotation and the geometry of its previous stellar encounter. If such an encounter occurred, a comet in a bound orbit around a star experiences seasons, with one hemisphere receiving more integrated sunlight over an orbital period depending on the tilt of the rotation axis. Seasonal differences could lead to differential mantle development, but this requires the comet to have been in a bound orbit at some point, a scenario that is plausible but unproven. Another possibility involves primordial heterogeneity, differences that originated during the comet's formation and have been preserved ever since. Protoplanetary disks are not uniform. They exhibit radial gradients in temperature, pressure, and composition, and vertical stratification where dust settles toward the midplane while gas remains more diffuse. Material accreting into a comet could come from different disk locations or different vertical layers, resulting in a nucleus with compositional variations embedded at the time of formation. If one hemisphere accreted from a dust-rich region and the other from an ice-rich region, the observed asymmetry would be a fossil record of disk structure, a frozen snapshot of conditions in a protoplanetary environment billions of years old. Cryovolcanism, the eruption of volatile-rich fluids from the interior of icy bodies, has been observed on moons in the outer solar system, Enceladus, Europa, Triton, where tidal heating or radioactive decay provides energy to melt subsurface ice and drive eruptions. Cometary nuclei are too small for significant tidal heating and too depleted in radioactive isotopes for substantial radiogenic heating. But transient cryovolcanic events driven by pressure buildup from sublimation are conceivable. If the active hemisphere experienced such an event in the past, it might have excavated or fractured the surface, exposing fresh ice while leaving the dormant hemisphere undisturbed. The event would need to have occurred relatively recently, within the last few million years, Otherwise, sublimation and mantling processes would have re-equilibrated the surface. The dormant hemisphere might also be chemically altered in ways invisible to remote sensing. Cosmic ray bombardment over millions of years can create complex organic molecules, polymerize simple ices into refractory tholins, and alter the crystalline structure of water ice. If one hemisphere faced forward during the comet's interstellar journey, it would have received higher doses of cosmic rays and interstellar dust impacts, potentially transforming its outermost layers into a radiation-processed rind less prone to sublimation. Laboratory experiments simulating these conditions show that irradiated ices can develop altered thermal and mechanical properties. But the parameter space is vast and the connection to cometary behavior uncertain. Temperature measurements, if they could be obtained, would resolve many of these questions. Infrared observations can detect thermal emission from the nucleus surface, allowing direct measurement of temperature as a function of location and rotation phase. Such observations have been attempted but are limited by the comet's small size and faintness. The nucleus itself is lost in the glare of the coma, its thermal emission overwhelmed by reflected sunlight from dust. Longer wavelengths, in the far infrared or submillimeter, would penetrate the coma more easily and be more sensitive to thermal emission. But telescopes operating at these wavelengths have limited sensitivity and spatial resolution. The temperatures remain unmeasured, inferred only indirectly from models that are themselves uncertain. The silence persists. The dormant hemisphere continues its rotation, bathed in sunlight, absorbing energy, and yet remaining inert, frozen, inactive. It is a silence that speaks to the complexity of cometary physics, to the interplay of composition, structure, and thermal history, to the difficulty of inferring interior properties from surface observations. It took billions of years for the comet to reach this configuration. This particular arrangement of ice and dust and voids, it will take an unknown number of additional observations, additional missions, additional interstellar visitors before the silence yields its secrets, if it ever does. For now, it remains what it is. A hemisphere of ice that does not sublime, a mystery wrapped in dust, a question without an answer. Magnetic field interactions, or lack thereof, enter the discussion as researchers exhaust conventional explanations and begin exploring more exotic possibilities. Comets are not magnetic in the way that planets can be. They lack molten metallic cores generating dynamo fields, and their small size means that any remnant magnetization from their formation would be weak at best. But the solar wind itself carries a magnetic field, frozen into the outflowing plasma. And this interplanetary magnetic field can interact with the ionized gas in a comet's coma, creating induced magnetic fields and plasma boundaries that shape the flow of charged particles around the nucleus. The bow shock and magnetic draping around active comets have been studied by spacecraft missions, most notably at Comet Halley and more recently at 67P Churyumov-Gerasimenko, where the Rosetta orbiter carried magnetometers that measured field strengths and orientations with exquisite precision. These observations revealed complex interactions between solar wind plasma and cometary ions, the formation of current sheets and plasma instabilities, the acceleration of particles to high energies. But none of these interactions were observed to suppress outgassing on one hemisphere while leaving another active. Magnetic fields can deflect charged particles but do not directly affect neutral molecules or the sublimation of ice. Still, the possibility is considered. Could remnant magnetization in the nucleus itself, perhaps locked into iron-bearing minerals embedded in the ice dust matrix, create local magnetic anomalies that somehow influence sublimation? The physics is unclear, Magnetic fields can affect the trajectories of ions and electrons produced when solar ultraviolet light ionizes gas in the coma, potentially altering the local plasma environment above the surface. If plasma heating or cooling depends on magnetic field configuration, and if this somehow feeds back to influence surface temperatures, an asymmetry might result. But the chain of causation is tenuous, requiring multiple steps of interaction, each with uncertain magnitude and sign. Measurements of magnetic fields in cometary environments are rare and challenging. Spacecraft equipped with magnetometers must approach closely, within the coma or even near the nucleus surface, to detect the weak fields present. For an interstellar comet passing through the inner solar system on a hyperbolic trajectory, no such mission is feasible on the timescales of its discovery and observation. The comet will come and go before any spacecraft could be designed, built, launched, and maneuvered into position. Remote sensing offers no direct measurement of magnetic fields at cometary nuclei. The signals are too weak, the spatial scales too small. Inferences must rely on indirect evidence, on observations of plasma behavior or ion trajectories, which themselves are difficult to obtain for faint, distant objects. Another angle of inquiry considers the role of magnetic fields in the interstellar medium through which the comet traveled for millions of years. The galaxy is threaded with magnetic fields, weak by laboratory standards, but sufficient to influence the trajectories of charged cosmic rays and the dynamics of interstellar clouds. Could prolonged exposure to interstellar magnetic fields have magnetized the comet's nucleus, aligning magnetic domains in iron grains or inducing persistent currents in conducting pathways? The temperatures in interstellar space are far below the Curie temperature of most magnetic minerals, meaning that any magnetization acquired would be stable over geological time. But the process of acquiring such magnetization requires an external field strong enough and persistent enough to overcome thermal randomization of magnetic moments, and it is unclear whether interstellar field strengths are sufficient, even if the nucleus is weakly magnetized. Connecting this to the observed outgassing asymmetry requires a mechanism. One speculative possibility involves the interaction between the comet's magnetic field and the solar wind magnetic field as the comet approaches the Sun. The two fields could reconnect or interact in ways that preferentially heat one hemisphere through plasma currents or wave dissipation. But such heating would be expected to enhance outgassing rather than suppress it, and the dormant hemisphere shows suppression, not enhancement. The hypothesis struggles to match observations. Plasma physicists contribute to the discussion, bringing expertise in magnetohydrodynamics and collisionless plasmas, regimes where magnetic fields and charged particles interact in complex ways. They construct models of the plasma environment around the comet, solving equations that describe the flow of ions and electrons, the evolution of magnetic field lines, the generation of waves and instabilities. These models are computationally intensive, requiring three-dimensional simulations run on supercomputers, and even then they make simplifying assumptions about the properties of the coma and the boundary conditions at the nucleus surface. Results are suggestive but not definitive. Some configurations produce asymmetric plasma densities or temperatures, but none reproduce the stark contrast between active and dormant hemispheres observed in gas production rates. The lack of a clear magnetic mechanism does not rule out magnetic effects entirely, but it relegates them to the status of secondary factors, modifiers of behavior rather than primary drivers. If the asymmetry originates from compositional or structural differences, magnetic interactions might amplify or shape the resulting activity patterns, but they are unlikely to create the asymmetry from scratch. This is the conclusion reached by most researchers after exploring the possibility interesting to consider, difficult to test. probably not the answer, but worth keeping in mind as more data becomes available. There is a certain elegance to the fact that magnetism, a force that has shaped human technology from compasses to electric motors to magnetic resonance imaging, finds application in cometary science, however tentatively. The same Maxwell equations that govern electromagnetic fields in terrestrial laboratories govern the interaction between solar wind and cometary plasma. The same boundary conditions that describe current sheets in the magnetosphere describe the interface between ionized coma and neutral nucleus. Physics is portable, its laws valid everywhere, and even in the absence of a clear role for magnetism in explaining the interstellar comet's asymmetry, the effort to investigate is worthwhile. An exercise in thoroughness, a refusal to leave stones unturned. It took centuries to develop the theory of electromagnetism. It will take perhaps only a few more years to conclusively rule out or confirm its role in this particular mystery, depending on what the next interstellar visitor reveals. The journey before arrival, deep time in interstellar space, stretches backward through millions of years, an interval so vast that it dwarfs recorded human history and rivals the timescales of continental drift and biological evolution on Earth. The comet drifted through the galaxy at a velocity measured in tens of kilometers per second, a speed that seems rapid on human scales but translates into glacially slow progress across interstellar distances. Even at 30 kilometers per second, crossing a single light-year requires 10,000 years. The nearest stars are several light-years distant. The comet's origin, wherever it may be, is likely tens or hundreds of light-years away, meaning the journey consumed not thousands but millions of years of isolation. During this time, the comet experienced conditions unlike anything found in planetary systems. The temperature of interstellar space hovers just a few degrees above absolute zero, maintained by the faint glow of the cosmic microwave background, the relic radiation from the Big Bang that fills the universe uniformly. No sunlight warms the nucleus. No stellar radiation heats its surface. The comet is cold, profoundly cold. Its ice in thermal equilibrium with the surrounding void. At such temperatures, even the most volatile species, molecular hydrogen, helium, neon, would remain frozen if they were present, though these species likely escaped or never accreted in the first place due to their low condensation temperatures. Cosmic rays provide the only significant source of energy deposition. These high-energy particles, mostly protons accelerated to relativistic speeds by supernova shocks and other violent astrophysical processes, traverse the galaxy and strike the comet's surface with energies ranging from millions to billions of electron volts. Each impact deposits energy into the ice, ionizing molecules, breaking chemical bonds, creating radicals that can recombine into new species. The dose accumulates slowly but relentlessly. Over millions of years, the outermost centimeters of the nucleus are processed, their chemical and structural properties altered in ways that distinguish interstellar comets from their solar system counterparts that spend most of their existence in the relatively shielded environment of the Oort cloud or Kuiper belt. Laboratory experiments attempt to simulate this cosmic ray processing by irradiating ice samples with proton or electron beams, measuring the resulting chemical changes and physical modifications. The experiments show that simple ices like water and methane can polymerize into complex organic molecules, that crystalline ice can become amorphous, that trapped gases can be mobilized and lost to space. But the experiments operate on timescales of hours or days, compressing the dose rate by many orders of magnitude compared to the true interstellar environment. Whether the results scale correctly to geological timescales remains an open question, one that can only be answered definitively by studying objects that have actually experienced the full duration of interstellar exposure. Micrometeoroid bombardment adds another layer of surface processing. Interstellar space is not empty. It contains dust grains, small particles drifting between stars at velocities that can exceed 100 kilometers per second relative to the comet. Collisions with these grains excavate microscopic craters, sputter atoms from the surface, and gradually erode the outermost layers. The erosion rate is estimated from models of interstellar dust density and impact velocities, yielding removal rates of perhaps a few nanometers per million years. Over the comet's multi-million-year journey, centimeters of material could be lost from forward-facing surfaces, while trailing surfaces remain less affected. This differential erosion might contribute to the observed asymmetry, though the magnitude of the effect is uncertain and depends on parameters that are poorly constrained. Starlight, though faint in interstellar space, is not entirely absent. The galaxy is filled with stars, and their collective radiation creates a weak background illumination, the integrated starlight background that bathes all objects in a diffuse glow. This starlight is far too faint to warm the nucleus significantly, but it can drive photochemical reactions in surface ice, slowly modifying its composition. Ultraviolet photons, even at very low fluxes, can break molecular bonds and create radicals. Over millions of years, these reactions accumulate, altering the surface layer in ways that might affect its subsequent behavior when the comet enters a stellar system and begins to warm. The comet's trajectory through the galaxy was not a straight line. Gravitational perturbations from passing stars, encounters with molecular clouds, the tidal field of the Milky Way itself, all of these factors subtly altered the path over time. Each stellar encounter imparted a small velocity change, a deflection measured in meters per second or kilometers per second depending on the distance of closest approach. Some encounters might have been close enough to tidally stress the nucleus, pulling on it asymmetrically, potentially creating fractures or structural weaknesses. Others would have been more distant, their effects limited to small trajectory modifications. Tracing the orbit backward through these perturbations is essentially impossible without knowing the comet's complete trajectory and the positions and velocities of all nearby stars for millions of years. Information that does not exist and cannot be reconstructed. The isolation of the journey is difficult to convey. For millions of years, the comet experienced nothing. No encounters, no events, no changes except the slow accumulation of cosmic ray damage and micrometeoroid erosion. It drifted through darkness, through cold, through near-perfect vacuum. A frozen remnant of planetary formation processes that occurred in some distant star system at some distant epoch. Time passed, unmeasured and unmeasurable by any clock on the comet itself. Significant only in retrospect when the comet finally entered our solar system and became observable. There is a certain melancholy in imagining this journey. Billions of years of formation, accretion, evolution in a planetary system, followed by ejection into interstellar space through some gravitational slingshot or stellar encounter, and then millions of years of isolation before arriving here, now, where telescopes notice it and observers attempt to understand it. The comet is a messenger, but the message is written in a language we are only beginning to learn, encoded in asymmetries and chemical compositions and rotation states that hint at but do not fully reveal the conditions of its birth and the experiences of its journey. It took millions of years to arrive. It will take perhaps decades or centuries to decode the message. If we are diligent and fortunate, and if the next interstellar visitors cooperate by providing comparison data, models fail to converge on a single cause. A disappointing but perhaps inevitable outcome given the complexity of the system and the sparseness of constraints. Research groups around the world develop independent models, each incorporating different assumptions about nuclear structure, composition, thermal properties, and rotation state. Some models emphasize porosity variations, others, compositional heterogeneity. Still others invoke dust mantles or subsurface layering. The results are diverse. Every model can reproduce some aspect of the observations, the overall asymmetry, the dust-to-gas ratio, the spectral characteristics, but none captures all features simultaneously with parameters that are independently justifiable. The problem is fundamentally one of degeneracy. Multiple physical configurations can produce similar observational signatures, and without direct measurements of the nucleus itself, its shape, density, composition, temperature distribution, it is impossible to discriminate definitively between competing scenarios. Observations provide a limited set of constraints: gas production rates as a function of time, dust brightness and spatial distribution, rotation period, spectral composition. These are essentially boundary conditions, surface-level information that must be inverted to infer interior and structural properties. The inversion is non-unique, a mathematical reflection of the fact that we are trying to solve for many unknowns with relatively few equations. Statistical fitting techniques are employed, algorithms that search parameter space to find combinations that minimize the difference between model predictions and observations. Bayesian inference frameworks assign probabilities to different parameter values, updating beliefs as new data arrives, Markov chain. Monte Carlo methods sample the posterior distribution, exploring the high-dimensional space of possible nucleus properties. These techniques are rigorous and powerful, but they cannot overcome the fundamental limitation of insufficient constraints. The result is broad posterior distributions, wide uncertainties, parameter values that span ranges too large to be physically meaningful. Some models incorporate stochastic elements, random variations in surface properties or outgassing efficiency to account for the unpredictability observed in real comets. Jets turn on and off, outbursts occur without obvious triggers, activity levels fluctuate in ways that resist deterministic explanation. Adding stochasticity improves model fits, but at the cost of predictive power. A model that can adjust itself to match any behavior is not particularly useful for understanding underlying physics. The challenge is to distinguish between true randomness, arising from chaotic or turbulent processes in the coma or subsurface, and apparent randomness, arising from our incomplete knowledge of initial conditions and driving mechanisms. Collaborative efforts attempt to reconcile different modeling approaches, bringing together researchers with expertise in thermal physics, gas dynamics, dust transport, and plasma interactions. Workshops and conferences facilitate comparison of results, identification of common assumptions and divergent predictions. These efforts reveal that disagreements often stem not from fundamental physics, but from choices about boundary conditions, numerical resolution, or the treatment of poorly constrained parameters like thermal conductivity or dust grain size distribution. Standardizing these choices helps, but it cannot eliminate the underlying degeneracy problem. Null results are as informative as positive detections, though less satisfying. The absence of detectable magnetic effects, the lack of spectral features indicating exotic chemistry, the failure to observe splitting or major outbursts, all of these non-observations constrain the parameter space, ruling out extreme scenarios and focusing attention on more mundane explanations. Science often proceeds by elimination, narrowing the range of possibilities even when the single correct answer remains elusive. The interstellar comet's asymmetry is not explained by exotic processes, not driven by phenomena outside the standard repertoire of cometary physics. It is something ordinary, something that should be understandable, and yet it remains just beyond the reach of current models. Comparison with solar system comets provides context but not solutions. Many solar system comets exhibit asymmetric activity jets emerging from specific latitudes, seasonal variations in gas production, hemispheric differences in dust content. But these asymmetries are often time variable, changing as the comet's orientation relative to the Sun evolves or as surface properties are modified by ongoing sublimation. The interstellar comet's asymmetry appears more stable, more locked in, as if determined by structural features rather than transient conditions. This difference is intriguing but difficult to interpret without more complete data. The peer-reviewed literature fills with papers presenting models, each carefully hedged with caveats and uncertainties, each acknowledging the limitations of current observations. Abstracts use phrases like consistent with, may indicate, suggests but does not prove. The language is the language of incomplete knowledge, of hypotheses that await testing, of results that are preliminary and subject to revision. This is normal in science, especially in the study of rare phenomena observed under less than ideal conditions. The interstellar comet appeared, was observed intensively for a few months, and then faded from view. The data set is finite. The opportunity for follow-up observations passed. What is published is what we have, and it is not quite enough. Future missions are proposed, spacecraft designed to intercept interstellar objects on short notice, capable of launching within months of discovery and reaching the target before it departs the inner solar system. These missions are technologically challenging and expensive, requiring fast launch vehicles, efficient propulsion systems, and instruments capable of making critical measurements during brief flyby encounters. Funding is uncertain. Timelines are optimistic. But the scientific motivation is clear only by directly observing an interstellar nucleus, measuring its properties in situ. Can the ambiguities and degeneracies of remote sensing be overcome? Until such a mission occurs, if it ever does, the models will continue to diverge, each one plausible, each one incomplete. The asymmetry will remain unexplained in the strong sense, accounted for by multiple competing theories, but confirmed by none. It took billions of years for the comet to form and millions of years for it to arrive. It may take decades more for a consensus explanation to emerge, and even that consensus may be provisional, subject to revision when the next interstellar visitor arrives and provides new data that either confirms current thinking or overturns it entirely. Science, like the comet itself, moves through space and time at its own pace, indifferent to human impatience. What the asymmetry reveals about planetary formation elsewhere begins to emerge not as a definitive answer, but as a set of possibilities, hints and suggestions about the processes that govern the assembly of icy bodies around distant stars. If the asymmetry is primordial, built into the nucleus during its formation, it encodes information about the structure of that ancient protoplanetary disk, its temperature gradients, its turbulent mixing, its radial and vertical stratification. Planets and comets form from disks of gas and dust orbiting young stars, disks that are not uniform but richly structured, with zones of different composition separated by condensation fronts, where specific molecules transition from gas to solid as temperature drops with increasing distance from the star. Water ice condenses beyond the snow line, the radial distance where temperatures fall below approximately 170 degrees Kelvin, allowing water vapor to freeze onto dust grains and accumulate into larger bodies. Carbon monoxide, being more volatile, condenses farther out beyond the CO snow line where temperatures drop below 20 to 30 degrees Kelvin. A comet forming near the water snow line would be water-rich and CO-poor. A comet forming beyond the CO snowline would contain both species in abundance. The interstellar comet's chemical composition, with moderate CO to water ratio, suggests formation in an intermediate zone, perhaps analogous to the region between Jupiter and Neptune in our solar system. A zone cold enough for CO ice but warm enough that water dominates. But disks are not static. Turbulence driven by magneto-rotational instability or other hydrodynamic processes stirs the disk material, transporting heat and mixing particles radially and vertically. This mixing can carry icy grains formed in the outer disk inward toward warmer regions, or conversely, can loft material from the midplane into the less dense upper layers where stellar radiation can affect surface chemistry. A comet accreting in such a disk might incorporate materials from multiple disk locations, creating a heterogeneous nucleus with regions of different composition and structure. The asymmetry observed in the interstellar visitor could be a fossil record of this mixing, a snapshot of the disk's complex dynamics frozen into solid form. Planetesimal collisions also shape nuclear structure. In the early stages of planet formation, kilometer-sized bodies collide at velocities ranging from gentle grazing impacts to violent shattering collisions. Gentle impacts can lead to accretion, sticking together to form larger bodies. Violent impacts fragment both participants, creating debris that may reaccrete or may be lost. A comet nucleus that formed through the merger of two separate planetesimals, each with different thermal and compositional history, would naturally exhibit internal heterogeneity. If the merger was incomplete, leaving a contact binary with distinct lobes, the asymmetry would be particularly pronounced. The ejection mechanism that sent the comet into interstellar space also provides clues about the planetary system of its birth. Comets are ejected through gravitational interactions, typically close encounters with giant planets that impart sufficient velocity to exceed the system's escape speed. This requires a planetary system with at least one massive planet, likely a gas giant comparable to Jupiter or Saturn in our system. The existence of such a planet implies that the system underwent significant dynamical evolution, with planets migrating, scattering smaller bodies, and reshaping the architecture of the system over millions of years. The interstellar comet is a product of this violence, a fragment of the planetesimal population that failed to accrete into planets and was instead cast out. Statistical studies of interstellar object populations attempt to infer the rate at which such objects are ejected from planetary systems and the total number that must be drifting through the galaxy. Early estimates, based on the detection of just one or two interstellar visitors, suggest that there are trillions upon trillions of such objects in the Milky Way, a vast population of planetary system debris distributed through interstellar space. If this estimate is correct, then planetary systems are profligate, ejecting far more mass than they retain, and interstellar space is not empty but filled with icy wanderers, most of which will never pass near another star and will remain unobserved for the age of the universe. The asymmetry itself, if it is common among interstellar comets, might indicate something systematic about planetesimal formation in general. Perhaps all planetesimals are heterogeneous on some level, their structure reflecting the chaotic accretion process, and what we observe in the interstellar visitor is not an anomaly, but the norm, typically hidden in solar system comets by subsequent processing and mantling. Alternatively, the asymmetry might be specific to objects ejected from planetary systems, a result of tidal stress during the ejection event or differential heating during a close planetary encounter. Distinguishing between these possibilities requires observing more interstellar objects, building up a statistical sample large enough to identify patterns and correlations. Exoplanet science provides complementary constraints. Observations of planetary systems around other stars reveal a diversity far exceeding what is found in our solar system. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. Super-Earths with no analogue among the planets. Systems with planets in resonant orbits or highly eccentric orbits. This diversity suggests that planet formation is not a deterministic process, with a single outcome, but a stochastic process with many possible outcomes depending on initial conditions and subsequent evolution. If planetary systems are diverse, the comets ejected from those systems should also be diverse, each one carrying the imprint of its particular formation history. The interstellar comet, then, is a messenger not just from another star system, but from another instance of planet formation. A data point in the cosmic ensemble of planetary system outcomes. Its asymmetry is part of the message, a detail that hints at complexity and variability in processes we have observed directly only in our own backyard. It took billions of years for planetary formation theory to be tested against observations of our solar system. It may take centuries to accumulate enough interstellar visitors to test those theories against the full diversity of planetary systems in the galaxy. The comet arrived at a moment when we are just beginning to ask these questions. Early enough that every observation is precious, late enough that we have the tools to notice and measure. The timing, like the asymmetry, is simply what it is, a contingent fact with no deeper meaning, significant only because we choose to find it so. The comet departs, fading beyond detection as it accelerates outward past the orbit of Mars, then Jupiter, then the boundary where solar radiation becomes too faint to drive significant sublimation. Activity diminishes as the nucleus cools, volatiles freezing back into solid form, jets sputtering and ceasing, the coma dispersing into the background of interplanetary space. Within months of perihelion, the comet is no longer bright enough for small telescopes. Within a year, even large professional instruments struggle to track it against the stellar background. The signal-to-noise ratio drops, integration times stretch to hours, and eventually the observation becomes impractical, not worth the competition for scarce telescope time when other targets promise richer returns. The final images show a faint smudge, barely distinguishable from cosmic rays and hot pixels, a ghost of the object that briefly commanded the attention of the astronomical community. Astrometric positions are measured with increasing uncertainty. Orbital elements refined one last time using the complete arc of observations, and then the tracking stops. The comet continues, of course, indifferent to whether we watch or not, following its hyperbolic trajectory out of the solar system and back into the interstellar medium from which it came. The departure is not symmetric to the arrival outgassing during the inbound leg altered the orbit slightly through the rocket effect, and the final trajectory differs by small amounts from what would be predicted by gravitational forces alone. Calculations project the future path. The comet will cross the orbit of Neptune in a few years, Pluto's orbit sometime after that, and eventually the heliopause, the boundary where solar wind pressure balances interstellar pressure and the Sun's influence formally ends. Beyond that, it returns to interstellar space proper, to the cold and darkness and isolation it experienced before. The velocity at infinity is slightly different now than it was on arrival, modified by the gravitational assist from the Sun and the accumulated momentum changes from asymmetric outgassing. The new trajectory will carry it in a different direction through the galaxy, toward a different region of space, potentially toward an eventual encounter with another stellar system millions of years hence. The departure trajectory is calculated backward as well, using the observed orbit to infer where the comet came from, which direction in the galaxy it approached from, whether any known stars lie near the backtracked path. The uncertainties are large, small errors in measured position and velocity amplify over the long time scales involved, and the gravitational perturbations from passing stars during the interstellar phase are unknowable. Still, statistical arguments can be made. The comet likely originated from a region of the galaxy where star formation occurred hundreds of millions or billions of years ago, where planetary systems had time to form, evolve, and eject debris. The specific star system remains unidentified and may be forever unidentifiable, lost among the hundreds of billions of stars in the Milky Way. Observers shift their attention to other targets, other phenomena, other questions. The interstellar comet becomes a dataset. Files stored in archives, tables published in journals, images preserved for future analysis should new techniques or theories suggest re-examination. The data is public, freely available, maintained by institutions dedicated to long-term stewardship of astronomical observations. Anyone with interest and skill can download the spectra, the photometry, the astrometry, and attempt their own analysis, develop their own models, propose their own interpretations. Science is, in this sense, democratic, open to reinterpretation and revision, never fully closed even when active observation ceases. Follow-up studies appear in the literature for months and years after the comet fades from view. Papers analyzing archival data, comparing the interstellar visitor to solar system analogues, refining compositional measurements, presenting new models or critiquing existing ones. The comet remains scientifically alive long after it becomes observationally dead. Its legacy carried forward in the questions it raised and the techniques developed to study it. Future proposals for telescope time and spacecraft missions cite the interstellar comet as motivation, arguing that understanding such objects is key to understanding planet formation, cometary physics, and the structure of the interstellar medium. The asymmetry, unresolved and unexplained, becomes a standard example in review articles and textbooks, a cautionary tale about the limits of remote sensing and the degeneracies inherent in modeling complex systems. It is taught to graduate students as an illustration of how observations constrain but do not uniquely determine theoretical models. It appears in conference presentations as a puzzle still awaiting solution, a challenge for the next generation of instruments and missions. The comet itself is gone, unreachable, but the mystery it embodied persists, embedded now in the collective knowledge and ignorance of the scientific community. There is something quietly appropriate about the fact that the comet's departure mirrors its arrival gradual, undramatic, a fading rather than an ending, no climax, no resolution, no final revelation. It came, was observed, and left, carrying its secrets with it. The universe is filled with such moments, phenomena that appear briefly within the narrow window of human observation, provide incomplete data, and then vanish, leaving behind more questions than answers. We are not entitled to complete understanding. We observe what we can, when we can, and accept that some mysteries will outlast us, preserved in data archives and unresolved debates, waiting for future insights or future visitors to provide the missing pieces. The comet moves outward, cooling, darkening, returning to the state it maintained for millions of years before entering our solar system. Its asymmetry, whatever its cause, becomes irrelevant again, significant only when solar heating makes it manifest, dormant otherwise. In the cold of interstellar space, there are no hemispheres, no active and inactive sides, only a frozen nucleus tumbling through the void, indistinguishable from countless others, anonymous and uncatalogued. One fragment among trillions in the galaxy's vast population of interstellar debris. It took billions of years to form and millions to arrive and only months to observe. Now it takes forever to depart, or what amounts to forever on human timescales, the slow drift into distances that render it forever beyond reach. Archival data and the wait for another visitor settle into a pattern of patience, a recognition that interstellar objects appear on timescales beyond human control, detectable only when they happen to pass close enough to Earth and when our instruments happen to be watching the right patch of sky at the right time. The first confirmed interstellar object, Oumuamua, was discovered in late 2017. Its unusual characteristics: extreme elongation, non-gravitational acceleration, lack of detectable coma, sparking debates that continue years later. The second, comet 2I Borisov, arrived in 2019, more conventionally cometary in appearance and behavior, though still distinguished by its extrasolar origin. The frequency of detections suggests that interstellar visitors pass through the inner solar system regularly, perhaps one per year or more, but most are too faint or too fast-moving to be noticed by current surveys. Next-generation survey telescopes promise to increase the detection rate. The Vera C. Rubin Observatory, with its large aperture and wide field of view, is expected to discover dozens of interstellar objects per year once it begins operations, scanning the entire visible sky every few nights and automatically identifying transients and moving objects. Other projects, operating in different wavelengths or with different observing strategies, will contribute as well. The era of rare, singular discoveries is ending, replaced by an era of statistical samples, populations large enough to identify patterns, correlations, and outliers. The asymmetric comet will have company, other interstellar visitors with their own peculiarities, their own mysteries, their own contributions to the growing understanding of how planetary systems form and evolve. Data archives grow, repositories that store not just the measurements themselves, but the metadata describing observing conditions, instrument configurations, calibration procedures. These archives are designed for longevity, maintained by institutions with mandates spanning decades or centuries, accessible through standardized query interfaces that allow researchers to retrieve specific datasets or cross-match observations from multiple sources. The interstellar comet's data sits in these archives alongside observations of stars, galaxies, asteroids, exoplanets, transient events, a vast collection of information about the universe organized and indexed for efficient retrieval. Future researchers, perhaps using techniques not yet invented, may reanalyze this data and extract insights that current analysis missed. Virtual observatory frameworks facilitate this reanalysis, providing tools for data visualization, statistical analysis, and model fitting. A researcher in one country can access data obtained by telescopes in another country, combine it with theoretical predictions or laboratory measurements, and publish results without ever physically traveling to an observatory. This democratization of access breaks down barriers, allowing contributions from anyone with skill and motivation, regardless of institutional affiliation or geographic location. The interstellar comet's data is, in this sense, a public good, freely available, maximally useful. Its value not diminished by being shared, but enhanced through multiple independent analyses. Lessons learned from the asymmetric comet inform future observing strategies. Rapid response protocols are developed to ensure that newly discovered interstellar objects receive intensive follow-up before they fade from view. Coordinated campaigns bring together observers across multiple continents and wavelengths, maximizing coverage and minimizing gaps in temporal sampling. Proposals are written for dedicated monitoring programs, for queue-scheduled observations that can be triggered automatically when an interstellar object is announced, for space-based missions that could provide continuous coverage uninterrupted by weather or daylight. The goal is to be ready for the next visitor, to learn from missed opportunities and marginal detections, to ensure that future datasets are more complete and better calibrated. Theoretical work continues in parallel, exploring parameter space through numerical simulations, developing new models that incorporate physical processes neglected in earlier studies, testing hypotheses that can be evaluated even without new observational data. Some of this work is purely academic, exercises in computational physics that may or may not connect to real objects. Other work is explicitly predictive, making specific forecasts about what future interstellar objects will look like if certain scenarios are correct. These predictions will be tested as new objects are discovered, confirming or refuting theories. Narrowing the range of viable models. The wait is not passive but filled with preparation. Calibration, development, instruments are upgraded, detectors replaced with more sensitive versions, software improved to handle larger data volumes and more complex analyses. Observers practice on solar system comets, refining techniques that will be applied to interstellar visitors when they arrive. Graduate students write theses on cometary physics, learning the field by studying objects that are accessible and well observed, building expertise that will transfer to the rarer and more exotic cases. The scientific community is, in a sense, training for an event whose timing is uncertain but whose occurrence is inevitable. Public interest ebbs and flows. The discovery of an interstellar object generates headlines, popular articles, television segments explaining the significance to general audiences. Then attention fades as the news cycle moves on, and the object becomes again the province of specialists, discussed in technical journals and conference presentations, but largely invisible to the wider world. This cycle will repeat with each new discovery, each one a brief moment of public engagement, followed by a long period of detailed scientific work conducted out of view. The comet cares nothing for this attention or lack thereof. It continues its trajectory, governed by gravity and momentum, unaware that it was briefly famous, unaware that its image appeared on screens and in print, unaware that its asymmetry puzzled researchers who will likely never see it again. Collaboration networks form and dissolve, groups of researchers coordinating on specific questions or datasets, then dispersing to other projects as interests shift and funding cycles turn. Some collaborations are formal, with written agreements and author lists negotiated in advance. Others are informal, conversations at conferences or exchanges of emails that lead to shared insights and co-authored papers. The interstellar comet becomes a nexus for such collaborations, a common interest that brings together people who might not otherwise interact, specialists in different subfields finding common ground in the puzzle of asymmetric outgassing. It took millions of years for the comet to arrive, but only months for a global community of researchers to coalesce around the challenge of understanding it, and only a few years for that community to begin dispersing again as other priorities emerge and the initial urgency fades. Silence returns to the ecliptic plane, the flattened disk of space where planets orbit and most solar system objects reside, a region that briefly hosted an interloper from beyond and now settles back into its familiar patterns. The asteroid belt continues its slow orbital dance, millions of rocky bodies circling the Sun in the gap between Mars and Jupiter, their trajectories governed by gravitational resonances and collisional evolution over billions of years. Comets from the Kuiper Belt and Oort cloud make their periodic approaches to the inner solar system, brightening and fading on schedules determined by their orbital periods, predictable and catalogued. The interstellar visitor is gone, its hyperbolic trajectory carrying it away from the plane, out of the Sun's gravitational dominance, back into the three-dimensional space of the galaxy where orbits are not flat and motion is governed by the collective gravity of billions of stars. Telescopes return to their regular programs. Surveys that scan the sky for near-Earth asteroids. Photometric campaigns measuring stellar variability. Spectroscopic studies of distant galaxies. The observing schedules fill with targets chosen months in advance, proposals reviewed and ranked by committees, time allocated according to scientific merit and technical feasibility. The interstellar comet was an interruption, a target of opportunity that justified deviations from planned observations. But such opportunities are finite and eventually exhausted. Normal operations resume. The sky is vast, and there are always more objects to observe, more questions to answer, more data to collect. The data themselves remain archived and indexed, reduced from raw photon counts to calibrated spectra and images, published in tables and figures that summarize months of observation in compact form. These data will outlive the comet, which even now is fading into unobservability. Its reflected light too faint to distinguish from background stars, its thermal emission too weak to detect at the distances it has reached. The comet is physically intact, presumably continuing to exist as a solid object, but it has become observationally extinct, beyond the reach of current instruments. In this sense, the data are more real than the object they describe, more accessible, more permanent, artifacts of measurement that persist while the measured system recedes into darkness. Scientific papers age in their own way, cited frequently in the first few years after publication, then less frequently as the field moves on and newer results supersede older ones. Review articles synthesize the literature periodically, distilling dozens of papers into coherent narratives, identifying consensus where it exists, and highlighting controversies where it persists. The interstellar comet will appear in these reviews for decades, an example of asymmetric outgassing, a case study in observational challenges and modeling ambiguities. Eventually, as more interstellar objects are discovered and studied, it will become one entry in a table, one point in a scatterplot, distinguished only by being among the first, no longer unique but part of a population. The mystery of the asymmetry may resolve or may persist. Future discoveries might reveal that asymmetric outgassing is common, a natural consequence of nucleus heterogeneity, in which case the interstellar comet's behavior will seem less puzzling in retrospect, or future objects might all behave symmetrically, making the asymmetric comet an outlier, an anomaly that demands special explanation. Without a larger sample, it is impossible to know whether the phenomenon is typical or exceptional, a question that can only be answered statistically, through accumulation of cases, through comparison across multiple objects with different properties and histories. There is a rhythm to astronomical discovery, a pattern that repeats across different phenomena and different epochs. First, the surprise something unexpected appears, violating assumptions or defying easy explanation. Then, the intensive study instruments are turned toward the phenomenon. Data accumulates, models are proposed and tested. Finally, the integration. The phenomenon is understood, or at least categorized, placed within a broader framework. Its strangeness diminished through familiarity. The interstellar comet is somewhere in the transition between intensive study and integration, no longer entirely surprising but not yet fully understood, occupying a liminal space where questions outnumber answers, but progress is being made. Night sky observations continue. Amateur astronomers and professionals alike pointing telescopes upward, capturing photons that have traveled across space to reach Earth's surface. Most of what they see is familiar stars in their constellations, planets moving against the zodiac, the moon waxing and waning through its phases. Occasionally, something new appears. A nova or supernova, a bright comet, an asteroid on close approach. These events break the routine, inject novelty into the predictable, remind observers that the universe is dynamic, active, filled with processes operating on timescales from seconds to eons. The interstellar comet was such an event, a brief intrusion of the exotic into the mundane, and now it has passed, leaving behind its dataset, its mystery, its small contribution to the accumulated knowledge and ignorance of astronomy. Silence is not absence, but a return to baseline, to the steady hum of ongoing processes, the slow accumulation of observations and insights that characterizes science in its normal mode. The ecliptic plane was never truly silent. Planets orbit, asteroids tumble, solar wind streams outward, cosmic rays penetrate inward, a constant traffic of particles and fields and radiation. What has ceased is the particular signal of the interstellar comet, the specific pattern of outgassing and reflected light that marked its presence. That signal is gone now, dissipated into the background, irretrievable except through the data archives where it is preserved in digital form. The comet itself continues, unknowing and unfeeling, a physical object obeying physical laws, cooling as it recedes from the sun, freezing as temperatures drop below the sublimation points of even the most volatile ices. Its rotation persists, angular momentum conserved in the absence of significant external torques. Its trajectory is fixed, determined by the velocity and position it possessed at the moment it left the observable region, extrapolated forward through gravitational calculations that assume no further perturbations. In reality, perturbations will occur distant stellar encounters, passage through molecular clouds, the tidal field of the galaxy, but these are negligible over the timescales of centuries or millennia, significant only over millions of years when the comet has long since vanished from human memory. If human memory even persists that long, it took billions of years for the atoms in the comet to form, to condense from interstellar clouds into a protoplanetary disk, to accrete into a solid body. It took millions of years for that body to cross the galaxy and arrive here. It took months for us to observe it. It will take billions more years for the comet to encounter another stellar system. Perhaps it will drift through interstellar space indefinitely, never again approaching close enough to a star to outgas, remaining frozen and inert for timescales that exceed the current age of the universe. Its story, such as it is, has no ending, only a fading, a gradual loss of relevance and accessibility, a drift into the vast indifference of deep space and deep time. The sky holds the comet no longer, and the questions it carried recede with it into distances beyond naming. Somewhere far from the sun's warmth, the nucleus tumbles in darkness, its asymmetry irrelevant now, its ice locked in cold that knows no seasons, no change, no observation. The data remain, ones and zeros preserved on spinning disks and solid-state arrays, but the object itself has returned to anonymity, one mote among countless others drifting between the stars. Telescopes turn away. Observers sleep. The instruments cool in their domes, awaiting the next night's targets, the next round of exposures and integrations, the patient accumulation of photons that is the substance of astronomy. The mystery persists, quieter now, less urgent, a footnote in ongoing research rather than a headline, a problem deferred rather than solved. Perhaps another visitor will arrive, carrying answers or deeper questions. Perhaps not. The universe is under no obligation to provide clarity on human timescales. Deep time stretches in all directions backward to the comet's formation in some nameless stellar nursery, forward to its continued wandering through the galaxy's spiral arms, outward to the billions of other star systems where similar processes play out unseen and unrecorded. The asymmetry was a detail, a small variation in a system already small and distant. That it caught attention at all is perhaps the greater mystery. The fact that minds on one particular planet chose to look, to measure, to wonder about ice and gas, and the way sunlight warms surfaces that will never be visited. Night settles over observatories, over cities, over the curve of Earth's surface as it rotates beneath fixed stars. Somewhere in archived files, the comet spectrum glows faintly on a screen no one is watching. Somewhere in the outer solar system, its nucleus continues outward, patient and oblivious. And somewhere in the space between, the questions drift, unanswered, carried forward into whatever future may attend them, if any future does at all. The silence is not empty. It is simply silent, the way space has always been silent, filled with light and matter and motion, but offering no commentary, no explanation, no resolution. Only the steady, patient drift of things through darkness, the long exhale of deep time, the quiet persistence of ice and stone and mystery, moving through the void as they have always moved, as they will continue to move, long after observation ceases and memory fades, and even the questions themselves dissolve into the patient stillness of the cosmos at rest.